So in this video, we're going to discuss average rate of change. An average rate of change is really just a better term for slope because it tells us more about what's happening in the context of a word problem. So the average rate of change is calculated by doing the change in the outputs over the change in the inputs. So f of b minus f of a over b minus a. Or sometimes you'll hear this referred to as delta f, that little triangle, delta f over delta x. That just means change in f over change in x. And so the reason I'm saying this is very similar to slope, if you recall, the slope m equals y2 minus y1 over x2 minus x1. And what that's really showing is the change in the outputs. Y2 and minus y1, those are outputs. X2 and x1, those are inputs. So essentially when you're calculating slope, that's what you're finding. Change in outputs over change in inputs. The average rate of change is good for describing real-world problems. So when you calculate the average rate of change, you want to make sure that you note the units, which will always be whatever the output is, f, per 1 unit of x, or the input. And we'll see how that works in a little bit. And so the idea is that when the average rate of change is positive, the function is increasing, right? If you have a positive slope, some sort of positive slope, then the function is increasing. But if you have some sort of negative slope, the function would be decreasing. So let's look at an example where we're going to calculate some average rates of change. The table below shows the winning pole vault heights from 1960 to 2000, but we've got a little gap here, so we've really got kind of the beginning of tracking this data and the end of tracking this data with the little gap in between. So what is the total change in height of pole vaults from 1960 to 1968? Or we're looking at how much has this winning height increased. So I would say, well, then 213 minus 185 would be 28 inches. So the winning height has increased 28 inches from 1960 to 1968. So thinking about that, then, the average rate of change should be some positive number. So if we want to compute the average rate of change from 1960 to 1968, we want to look at the change in the outputs over the change in the inputs. So the change in the outputs, we've actually already calculated that. Here are the outputs. In 1968, 213, and in 1960, 185. So 213 minus 185 would be the change in the outputs. 1968 and 1960 would be the inputs. So 1968 minus 1960 gives us 28 over 8, which equals 3.5. And notice that I said include units. The units are always the output per 1 input. So this would be 3.5 inches per year. What that is showing is that on average, the winning height is increasing by 3.5 inches per year. So what is the average rate of change from 1992 to 2000? So the change in the outputs, in 2000 the output's 232 minus 1992's output is 228 over the inputs 2000 minus 1992. That gives us 4 over 8, which is 0.5 and our units would be inches per year. So what this is showing is that the growth, the amount that the winning height is increasing from 1992 to 2000 is not nearly as much as from 1960 to 1968. In other words, people are not improving their height as much in these later years. So we've looked at a table, and now we're going to look at a graph. So this graph below shows an object's distance from a point at a time in t seconds. And we want to find the average rate of change from t equals 0 to t equals 3. So notice this function is t, and the output's s of t. So when t equals 0, we want to figure out what is s of 0. That would be that point there. S of 0 is 1. So my output is 1 when my input is 0. When t equals 3, s of 3 would be this point right here. When the input is 3, the output is 4. So the average rate of change would equal the change in the outputs, 4 minus 1, over the change in the inputs, 3 minus 0. So that would give me 3 over 3, which equals 1. But what units are that? The units are always the output per the input. So the output is meters. So 1 meter per the input, which is seconds. What this is actually showing is a speed that this particle, or this object I should say, has an average speed of 1 meter per second. And what we've actually shown is an important idea, which is average velocity. Something's average velocity, if we think of velocity kind of similar to speed, is an object's change in position over change in time. So if you think about a car, what is the average velocity of a car that travels 200 miles in 4 hours? Well, it changed in position by 200 miles. It went 200 miles divided by 4 hours. We know that that car is traveling 50 miles per hour on average. Now let's look at an example where we're only given a function. We're not actually given the outputs, and we need to go ahead and find those outputs. This says the amount of people infected with the virus is a function of time since scientists noticed the problem. The number of people infected I can be determined by the function I equals 2000 times 1.05 to the power of t, where t is the number of hours since the virus was noted. Calculate the average rate of change from t equals 1 to t equals 4. So we're given inputs, but the problem is we don't yet know what the outputs are. So we actually need to come up with the outputs in this situation. So let's say t equals 1. We need to figure out what I is when t equals 1. So that would be 2000 times 1.05 to the power of 1. And that gives us 2100. Meaning at 1 hour, 2100 people are infected. When t equals 4, I equals 2000 times 1.05 to the power of 4. And just for this case, since we notice, these are people, I'm going to round to the nearest whole number, which is 2,431. So that's another point. 4, 2,431. So let's calculate the average rate of change then. The average rate of change would equal the change in the outputs, 2,431 minus 2,100, over 4 minus 1. That gives us 331 over 3, which is about 110.3, and then you'll notice that's repeating. So I would say that, since we're again talking about people, that's 110 people infected per hour. So we want to think about, what does this mean in the context of the problem? Well, the rate of change would change with different time periods. So we want to note that this specific rate of change is from 1 to 4 hours. So what I would say is from 1 to 4 hours, 110 people are infected per hour on average.